Joule's experiment is shown below, where a helium gas is placed in container A, which is shut off from container B with a stopcock. Now container B is evacuated, and both containers are placed inside a calorimeter. So we have this fluid in the calorimeter and a thermometer to measure the temperature. And part A asks us, when the stopcock is opened, the gas flows to container B, and the thermometer shows a negligible change in temperature. And let's explain why using the first law of thermodynamics. So the first law tells us that the change in internal energy is equal to the heat plus the work. And remember that using our kinetic molecular theory, we saw that the average kinetic energy of a gas, and particularly an ideal gas, is proportional to the temperature. So therefore the temperature is the internal thermal energy of the gas. And because the temperature did not change, then effectively the change in internal energy is zero. And we conclude that the internal energy is a function of the temperature only. So what we end up with is 0 is equal to Q plus the work. Now because the volume of gas expanded, then this here is the work done by the system or by the gas on the surroundings. And therefore the work is a negative quantity. So therefore heat must have flowed into the system such that the change in internal energy is 0. And we had an isothermal expansion basically, where the temperature remained constant. Now let's look at question B. So if neon gas is placed with the helium gas inside container AB with the stopcock removed, okay, so what we have is our neon gas mixed in with the helium. What is the ratio of kinetic energy of both gases in the mixture, assuming they are in thermal equilibrium? And we're told that the molar mass of neon is higher than that of helium. Well, in this case, we expect that the ratio of the kinetic energy of helium to the kinetic energy of neon to be equal to 1. Because both gases are in thermal equilibrium, so therefore they must have the same internal energy, given that they have the same temperature. Now part C asks us to sketch the Maxwell-Boltzmann distribution for both gases, and we'll plot the number of gas particles against the velocity. And identify the root mean square velocity of both gases. Well, given that the molar mass of neon is higher than helium, so let's just start off by drawing the Maxwell-Boltzmann distribution of neon. So it looks something like this. And because the temperature of both gases is the same, then so is the average kinetic energy, and therefore the distribution of velocities for particles with a higher mass is going to be narrower than the particle with a lower mass. So therefore the Maxwell-Boltzmann distribution of helium is going to look something like this. And therefore the root mean square velocity for neon is going to be somewhere here. And the root mean square velocity for helium is going to be somewhere here. So remember that the root mean square velocity was equal to the square root of 3 by Boltzmann's constant by the temperature on the mass of the particle. Now given that the mass of the neon particle is higher than that of helium, then therefore neon's going to have a lower root mean square velocity compared to helium. And I'll see you in the next video.